We all know there's an urgency to address harmful emissions from human activity. But fortunately for us, what contributes to global warming and what can be done to reduce it has never been so thoroughly understood. Now, one of the main culprits here is CO2. And in an International Energy Agency, so an IEA report, it was given that the energy-related global CO2 emissions in 2022 was a record-breaking 36.8 gigatons. But a gas that often isn't talked about in this conversation is methane. So in today's episode, that is what we're going to be hearing about: methane. Joining me today are Jacques Mulbert, the President of Measurement and Analytics at ABB, and Stéphane Germain, the Founder and Chief Executive Officer of GHGSat, whose technology are providing revolutionary ways to monitor emissions. But first, let's start with the basics. I asked David T. Allen, who is the Gertz Regents Professor of Chemical Engineering and the Director of the Center for Energy and Environmental Resources at the University of Texas. What is methane and why is it something that we should be looking at?
Methane is a greenhouse gas. It's the molecule CH4, so one carbon atom, 4 hydrogen atoms. And it comes into the atmosphere from a variety of sources. Methane is the principal component of natural gas, 97 or so percent. It's also the molecule that's released by cows, ruminant animals, and by wetlands and a variety of other natural sources. If we compare it on a mass basis and ask the question, how much warming is a kilogram of methane in the atmosphere causing relative to a similar amount of carbon dioxide? Kilogram of methane is equivalent to about 120 kilograms of carbon dioxide. So by a lot of different measures, methane is a really important greenhouse gas.
Isn't it just? And why hasn't there been as much attention on methane as there has been on CO2 in the climate change conversations?
One of the characteristics of methane is that it doesn't last in the environment as long as carbon dioxide does. So if we release carbon dioxide, it will persist in the environment for a century or more. In contrast, methane is what's referred to as a short-lived climate forcer. It'll slowly react away. And so when the thought was the majority of impacts from climate change will reach us by the end of the century, then the thought was any methane released today would be gone by the time we're worried about the effects of climate change. It would have reacted away and it wouldn't be as high a priority. But now, of course, we realize that the effects of climate change are already with us. They're already severe. And therefore, we need to focus on methane. We need to focus on these short-lived climate forcers.
So with this, I suppose, newly gained knowledge, what do methane emissions mean for our planet? And what does that mean for us as the people who live on the planet?
Well, let's look at the effect of methane emission warming relative to other types of warming from other types of human activity. And a metric that I like to use is to compare the warming effect to a certain number of cars. And so if we looked at the emissions of methane from the global energy sector, which are about 100 million tons a year of methane, and looked at the potency of methane over roughly a 20-year period or so, then the warming of that 100 million metric tons of methane would be the equivalent of about 8 billion tons of carbon dioxide. In terms of cars, if we could keep all the methane emissions from the energy sector in the pipe, that would be the equivalent of removing all the cars in the world off the road. It's probably the biggest single action that we can take in the short term to reduce the effects of warming.
I had no idea it had such a large impact, even if, no matter how short term it is. That is huge. And so where does it come from, methane? You've hinted at some of the sources of it, but where are the sources that we should be concentrating on?
Well, let's first just look at the difference between man-made and natural sources of methane. So of all the methane going into the atmosphere, about 60% is from man-made sources, anthropogenic sources. The remainder is natural, things like wetlands, termites, other types of sources of methane emissions. A third of the man-made emissions coming from the energy sector, and then 2/3 coming from agriculture.
And that makes sense. It's not that we shouldn't look at those other emissions, but it's actually like, let's concentrate on what we can change quickly, relatively quickly, with policy and within industry. But it's my understanding that methane has been increasingly monitored, let's say. And so how has the monitoring of methane improved our understanding of these emissions? And what has the implementation of that monitoring actually changed?
Our group here at the University of Texas made some of the first measurements of methane emissions from oil and gas chains that had been done in decades. And we found one major result in those initial measurements that really surprised people. If we look at the overall methane emissions and look in, for example, an oil and gas producing region, I'll use one of my home regions in north central Texas called the Barnett Shale. If you look at the Barnett Shale and ask where are all the emissions from oil and gas coming from, about half of the emissions are releases that were designed into the system. And we can act on those pretty quickly. The other half, though, came from what have come to be called super emitters. So these are large emission sources, largely associated with equipment malfunctions. Maybe it's older equipment, maybe it's broken equipment, but a large fraction of the total emissions comes from these malfunctions. And a big part of solving the methane problem is find those malfunctions, find them really quickly. And that turns out to be a pretty complex task.
You're absolutely right. And in terms of it, you were saying it's been an emerging technology over the last just 10 years and the differences that have come in that last decade. But also with this new technology is going to be a whole wealth of challenges, and not only technological challenges, but also political and legislation wise. But of course, these can only have a true effect if there are mitigations for lowering those emissions. And so what mitigations options do we have at the moment, and what do we hope to have in the future to actually make those changes that we're encouraging?
So the International Energy Agency made an assessment of how much would it cost to mitigate all the methane emissions from the global energy sector. And their analysis indicated that we could eliminate on the order of half of the global energy sector methane emissions at zero cost. In other words,
I was not expecting that answer at all.
In other words, the value of the methane and keeping the methane in the pipe as a product over a 2-year period would pay for the mitigation measure. And so it doesn't have a huge rate of return, and it's a lot, and very often it might be a lot of small sources, but in terms of cost, the mitigation measures are very frequently there and low cost. And so many organizations, many global major energy companies have announced that their goal is to get to zero methane emissions by 2030. And I believe that that's possible. I believe that we can get global energy sector methane emissions to near zero by 2030.
Thank you, David Allen from the University of Texas at Austin. And my word, that is a big target, but it is one that David thinks we can hit. But now let's turn our attention onto the critical topic of monitoring, because as David highlighted, this is what is going to show us where the problems are, which of course we need to know if we're going to effectively fix them and ultimately if we're going to make any difference to reducing those methane emissions around the world. Now, today we are here with Jacques Mulbert, president of ABB Measurement and Analytics. And I asked Jacques how they are going about monitoring methane emissions.
We're basically one of the leading suppliers of smart instrumentation and analyzers, including methane monitoring technologies. And we're also collaborating with governments and the industry. We decided together to develop basically an integrated methane monitoring platform. It's very important to standardize the way we measure methane emissions, and that's the target of this platform. So with this platform, basically the US will be able to continuously monitor the natural gas supply chain and its infrastructure, as well as putting the emphasis of any area and understand what's the state of the methane emission. This is a first of a kind and I believe a very interesting collaboration. This is a project of around 1 million, and it is 80% of it is financed by the DOE. So we do finance 20% of it, and gladly do so.
I suppose drilling down a little bit more into the detail, when it comes to actually monitoring methane, what different methods are there that ABB are implementing on a more large scale? What is it that you're up to right now?
Well, our technologies are widely used to monitor methane from space, land, and sea. Right? So let's step back first and go up to the space. Right? So basically,
why not?
Yeah, let's start with it. I mean, it's more original than the rest. We have technologies with extremely high resolution to be able to precisely measure emissions from space. Those sensors, which are infrared sensors that we send in the space, are able to measure particles per billions. And then there is a software that will reconstitute the impact on Earth. Okay, and that's our partners, our customers, etc., which are doing it.
Understood. So, yes, so you're the values you're taking, the readings you're taking are from space, but from that data you can sort of back extrapolate as to what has happened on Earth as to where they've come from.
Absolutely, and on the ground we basically manufacture solution to measure emissions from all oil and gas infrastructures. For example, pipelines. You might not know, but there are 1.1 million kilometers of gas pipelines. That's enough to go around the Earth 30 times. So that's very, very significant. Gosh. And a significant part of those pipes are buried. So measuring methane leaks from pipeline is absolutely critical. The oil and gas industry is responsible for half the methane emissions. 50% of emissions are coming from the pipeline. So basically what we have is a suite of solutions that measures, quantify, and map the methane emissions. And when I talk about a suite, it's because we have basically three kinds of solutions. So the first one, which we call the Hoover Guard, is basically drone-based. The second one, the Mobile Guard, is we have the analyzer fixed on a car. And the last one, the Micro Guard, is on a backpack and is monitored by a person. So what is it exactly? How does it work? What is it exactly doing? I take the example of the mobile guard, the analyzer fixed on the car. So basically, you have a laser analyzer, and I'll come back to the analyzer a bit later, in the car, together with an ultrasonic anemometer, because you need to measure the relative wind if you want to locate the leak when the car runs, right? You also have a satellite GPS. Obviously, you need to be able to record the location, so you need the GPS. And of course, you have the proper communication to send the data to the cloud, right? So basically, when the car is running, the analyzer detects the leak. It's a very specific analyzer. Mm-hmm. Basically, the way it works is that there is a tunable diode laser that is sending light at the right wavelength to interact with the gas. So it gives you extremely precise measures. So you take those precise measures, you take the data from the anemometers, you take the data from the GPS, and then the software computes the position of the leak and the size and a sizing of the leak. And this is sent to the cloud. That's the way it works.
Got you. So in terms of when it comes to monitoring the methane, the laser analyzer, in a way, analyzes the light fingerprint of the gases.
Yeah.
And then from that, you can determine whether there is methane in that mix. And then at the same time, you're measuring the wind speed, direction, and then also where you are with the GPS. And then you can send all of that data to the cloud, and then it can make it make sense by sort of transposing it onto, I suppose, either a color-coded or other way coded map of where it all is.
That's exactly it. It works the same way with the Hoover guard on the drone. Obviously, the Hoover guard is used for the difficult to reach pipelines of assets. Otherwise, you would use a car. And then you have the same material on a backpack to go and locate very precisely the leak. It is extremely important to have the same sensitivity with the backpack solution as with the two others. Otherwise, if you don't have the same sensitivity and precision, you will basically miss the advantage of the precision of the two other setups. Right? So this is the way it works. And this technology is very, very precise and very, very fast, much more than the conventional technologies that were pre-existing.
Understood. Gosh, this does not sound straightforward at all, but it sounds like you've been working on it, for the past 2 decades. And so you're on it, you're doing it. And can you talk us through how it works in practice? So yes, you've got your monitoring equipment there, you've spotted a leak with the system. Then what is the process? What happens?
Right. So the best is to take an example. And I will take an example with 2 advantages. It evidences the way it works, and it's also an example of an interesting collaboration. Right? So as those of us living in the US know, there are many abandoned oil and gas wells. If we listen to the EPA, there are around 3.7 million abandoned wells. 3.7 abandoned wells in the US. The regulation tells you when you own a well and you abandon it, you need to plug it to make sure that you have no more leakages. Unfortunately, there are 2 kinds of abandoned wells. One is the one which have an owner, and then they are usually plugged. And there are those which don't have an owner. And we call them the orphaned wells. Right? And those orphaned wells are open and leaking, and they are numerous. So it's quite complicated to estimate. We can read, different kind of estimation, but the evaluation that was made is that they generate between 7 and 8 million tons of CO2 equivalent per year in the US. So that's a concern of the authorities, and that's also a concern of some non-profit organizations. And we are working with one of those, and it's called the Well Done Foundation. And whatever application, it's the same. You start surveying, you start identifying a leak with the equipment, you fix, and then you monitor the fact that it is well fixed. So that's basically always the same process, which is very well evidenced with this cooperation with the Well Done Foundation.
Jack, it is absolutely fascinating this. When we started our conversation, I had kind of thought, with my pyrotechnics background of burning things, I was like, oh, it'll be the methane produced from combustion within industry. And I kind of hadn't even thought about pipelines. And now you're telling me about these orphaned wells and the massive negative contribution that they make to affecting our atmosphere. I'm somewhat flabbergasted by those facts that you've just said. But I suppose as well, going back to where I would have thought that methane monitoring was going on, I assume there is still methane monitoring going on within these, the gases that are released during combustion, of which methane is one. And how does that happen within industry?
Yes, you're absolutely right. Well, that's another technology. And basically what we have a technology which continuously measure the different gases that are coming out of the industrial stacks, right? Which is basically what you're talking about. So usually there is a combustion somewhere. There are some treatments, mixes, etc. So you end up with a number of gases that you need to understand.
And this is the continuous emissions monitoring systems, isn't it?
This is exactly it. So
yes, we've covered this before.
You would hear about SEMS, continuous emission monitoring system. So we are a leader in this field worldwide. And if you take a company like ours, we have an install base of 70,000 systems. So it's really widespread because there are regulations almost everywhere. And those regulations are becoming tighter and tighter. And
yes, that's quite rightly.
Yes, quite rightly, absolutely. That's an interesting area of cooperation between the regulators and the technology providers. And it can only work if all those different stakeholders work together, right? And that's very necessary because we need to scale up. We need to scale up R&D investment in order to be able to make a real difference in terms of global warming.
That was Jacques Mulbert, President of Measurement and Analytics at ABB. Now, there is no doubt how collaboration around reducing methane emissions is going to be key if the industry is going to get anywhere close to reducing their emissions and meeting their decarbonisation targets. And automation, of course, is at the heart of this story, processing all of that data that's coming in. Now, when it comes to monitoring, is there anywhere else that you get more data in than space? Which leads us on to our last guest of this podcast, who is from GHGSat, and it's Stefan Germain, the founder and chief executive officer at GHGSat, where they are indeed monitoring methane from space.
Well, GHGSat is a company that was founded for the purpose of monitoring greenhouse gas emissions from industrial facilities around the world. It was founded in 2011. And now we operate a constellation of satellites. We can measure emissions of carbon dioxide and methane right down to a facility level. So that means looking at everything from an oil and gas facility to a landfill to a coal mine, any major industrial source of methane. And we will soon be able to do the same sort of thing with carbon dioxide. That satellite was just launched recently. So we have 12 satellites in orbit now. We're detecting millions of tons of methane per year, and we're doing that all over the world.
And so with your satellites that are up there in orbit as we're speaking, how do they and you know where to look and search for the methane emissions?
Well, we start with UN reports. It's really quite simple. We start by looking at where climate change experts around the world have been finding major sources of emissions. Then look for publicly available information on those types of sources in those markets. And from those, you can typically just get GPS coordinates. When we can't find a GPS coordinate very easily, then we can use another wonderful resource, Google Maps, and use that to then track down individual facilities.
Got you. And in terms of the satellites themselves, in my head, I'm imagining something huge, this dish the size of a car, but that's kind of not what we're talking about here, is it?
No, it's not. So that's right. Most people, when they think of satellites, think about these billion-dollar things that are the size of a school bus or a car. In our case, we're talking about something the size of a microwave oven.
Okay, so how do they work? How do they do what they need to do? And how has ABB helped to develop the technology that they use?
Well, so there's three major components to launching any satellite. So the first and the most important is the sensor. And that's where we work very closely with ABB. The sensor then goes it's a part of a bigger satellite. So the sensor will be kind of put into the microwave oven, and that microwave oven is then the satellite here in that analogy. And then the third is the rocket to get us up to orbit. And for that, we typically use SpaceX. So what ABB does with us is they help us by manufacturing our instrument. The technology is an interferometer, and what it does is it looks for the absorption of light at very specific wavelengths that correspond to the presence of a greenhouse gas, either methane or carbon dioxide, on the ground. This spectrometer is kind of like detecting the fingerprints of methane. It's looking for the spectroscopic absorption of light due to the presence of the gas. And that unique fingerprint is what we use then to detect whether the gas is there and in what quantity. It's also, the sensor is also designed to have very high resolution, and that's very unique in the world. We, from the beginning, wanted to use a sensor from space to look right down to individual facilities. So if we could detect an emission from an individual oil well or from an individual landfill, we wanted to be able to discern that it was really from that oil well and not something next to it, or from that landfill and not something next to it. So the high resolution is really, really important as part of this sensor. So all of that is what ABB manufactures for us to our design specifications and to our system design. And we've got a great partnership.
Absolutely. And there's so many parties working together, just even when it comes to reporting if you find a leak. So in terms of all the processes together, how important is collaboration?
Well, collaboration is key. This is a very complicated system working on a global basis. Working with groups like the European Space Agency, NASA, even the Environmental Defense Fund, and others is really important to sharing, disseminating, validating a lot of the information, and ultimately driving to the action that we all want to reduce greenhouse gas emissions around the world. One thing I will highlight, though, is through all that collaboration, we think it's really important to work with operators to reduce their emissions and not to publicly shame them. We feel that we will get ultimately more impact, more reductions in emissions by working as a partner with our customers.
And it's that reduction in emissions that is the future that we're all looking towards, isn't it? So in terms of continuing that future gazing, what are your hopes for the future, both in terms of the technology that ABB develops and this movement to reduce the global emissions of methane and the other harmful emissions?
So we set up a specific target for ourselves. We, last year in 2023, mitigated 6 million tons of carbon dioxide equivalent in 1 year. So that's the equivalent of taking more than 1 million cars off the road for a year. And our ambition is to get to about 50 million tons of emissions per year mitigated. So that's like taking 20 to 30 million cars off the road every year. So we're at 6 million tons last year. It's a start, but we've got a long way to go. And so getting now to how ABB can help us do that, well, it's basically to help us put more sensors into orbit, and also to help us push the technology, to really take the technology to the next level in reducing our detection threshold, increasing the performance of the sensors so that we can detect smaller and more emissions all over the world and help accelerate the impact that we all want to have in the fight against climate change.
And what a great goal to have. But just before we go, Stefan, how on earth did you get into this?
It is quite a niche, isn't it? So I actually have been wanting to do this for an awful long time. So I've always had a passion since I was just a little boy to do things in space that could help down on Earth. And from the time I can remember playing with Legos when I was a kid, I was building space stations and things about space. The environmental side really came around in my university years when I became aware increasingly of the damage we as humans are doing to our own environment and the impact that we're having on our own climate. And so I was looking for an opportunity to bring the two of those together, literally for decades. 20 years ago, to do things in space, it took hundreds of millions of dollars, if not billions of dollars, to think about launching your own satellite. But as of 2006, a lot of things were changing really rapidly in the miniaturization of technology. And that's when I finally got the opportunity to see that things have miniaturized enough that maybe I could. And so it all came together really in 2010. And there was, the famous light bulb moment when I heard about a scheme for putting a price on a ton of carbon. And that's when I woke up to the fact that you could actually put a price on a ton of emissions, and companies would understand that as a financial risk. And so people should pay for understanding what their real emissions are. So long story, but I've been at this for a long time. This is really a culmination of a long plan to do what I'm doing today, and I'm thrilled to do it.
Gosh, what a journey I've gone on in this episode, and hopefully you have too. Learning how much methane is being emitted and what a difference it'll make if we reduced those emissions, and all the angles of which we're monitoring those emissions from. But unfortunately, that is it for this episode. Of course, a massive thank you to our guests, David Allen, Jacques Mulbert, and Stefan Germain. I'm Fran Scott, and the Process Automation Podcast is a Fresh Air production for ABB. Follow now from wherever you get your podcasts so you never miss an episode.